we're going to look at the exceptions. The exceptions are things like this. And people were asking me about this already. You were going, what happens when I have an when I have an asymptote? Now, where is the asymptote? So first of all, let's talk about this. So for this function here, I know that there's an asymptote. So again, it doesn't ask you to graph it. I'm going to just do a little sketch for myself. So I'm going to do a little sketch over here, not too big, because I want to answer it over here. So I'm going to do this. Okay, I know for this graph, so I don't want you, so what I talked about in the last examples from the other page were that I don't want you to forget what you already know. You know what a linear looks like. You know what a quadratic looks like. You know what a reciprocal function looks like. This reciprocal function has an asymptote where?
2.
At 2. So we know, okay, rough sketch. We know there's still a horizontal one here, and it looks something like this. Okay, so we know that at 2, that's a special number. At 2, that's an asymptote. So if I ask you the limit as x approaches 2, you know that what's happening when you're walking from the left and the right, so remember you're going from this way. So as I'm tracing the graph, I'm falling down this way. And I'm going for this way. And again, what do I mean by approaching? So if x is 2, this is this line. The yellow line is the line I'm approaching. From both sides of the graph, from the left and to the right, I'm walking, so I'm tracing the line and I'm going whoosh, and I'm heading down. So on the left side, I'm heading downwards, and on the right side, I'm heading upwards, right? So when I write this, I say the limit as x approaches 2 from the left. Now, you can write the function here. So I'm going to write the function, so 1 over x minus 2. So make sure you tell me what you're limiting. So I'm limiting that function. That will equal negative infinity. So it's heading downwards. As I'm heading from the right, I'm going to write the limit as x approaches 2 from the right of the function, x minus 2. So from the right, I'm heading upwards this way, so I'm going to be heading to infinity. I sometimes get people who ask me this. What happens if I had a function and both of them were heading upwards? Right? So what happens if it was infinity, infinity for both? What happens with this one? What's my conclusion? It's heading down to negative infinity, heading up to infinity, therefore does not exist, right? So therefore, the limit as x approaches 2 for the whole function, so that means both sides, equals does not exist. It does not exist unless the left and the right, the definition that we did is that the left and the right have to be approaching the value L, right? We used L to represent the value we're approaching. These are not approaching the same value. So that's approaching negative infinity, that's approaching infinity, therefore it does not exist. If it was this and both were approaching infinity, what would my answer be? No, it would still be does not exist. Infinity is not a number. Am I going to meet up at infinity? No, I'm never going to meet up at infinity because we never stop. So it's the idea of when we're approaching, and I use the idea of usually we're both approaching the same chair. So whether or not the chair is there or not. So we had this where I took the chair away, we both approached, it's missing. I can fill in the dot, the chair is there, we both approach the same chair. I can take the dot and do the same thing, move the chair, but I'm still approaching. We're both approaching the same thing, and I took the chair and threw it away, right? So it doesn't matter as long as left and right are approaching the L. So our definition was this. The limit as x approaches, whatever that value is from the left, has to equal L, which also is the same thing as x approaching a from the right of that same function. It has to be a value L. Infinity is not a value that we can meet at, so that is not a single value. They are both the same infinity, however, it's still not a limit. So you still say that the limit does not exist. Yeah?
So when it's a reciprocal, it's always D&E?
No. So the question is, if it's a reciprocal, it always does not exist. No, I was going to get to that, so give me 1 second. Okay, so does that make sense? So whether it's infinity, negative infinity, or both infinity, does not exist. Good?
Yes,
okay. Yeah.
So how come we write the limit as x approaches 2 from the right equals infinity?
It actually does not exist, but we're being more specific. We're actually saying that it doesn't exist, but I know what's happening with the pattern. So the pattern is that it doesn't exist, but it's approaching infinity. So you're explaining what's happening to it, not just saying it doesn't exist, right? So you could say it doesn't exist, but it's also approaching infinity. That's why it doesn't exist. So to be more concise, we just go it's infinity, right? But it's understood that infinity does not exist. Yeah. Okay. Yep.
Couldn't you do the same thing for the other limit then too? If you say it's infinity, that means it doesn't exist?
Sorry, could I do the same thing for which,
For
sorry?
the limit where you're approaching from both sides.
Yeah, but I don't want you to. I want you to explain using the infinity. So you're explaining. So you're being more precise by saying it doesn't exist, but it's this. This is what's happening. So we're talking about the infinite limit versus a point jump limit, right, and stuff like that. So we're trying to be more specific in our answer. Yeah, exactly. Okay, does that make sense? So it doesn't exist, but you're telling me why, right? So you're saying it there. Here you're saying it doesn't exist because I just explained with the two one-sided that's why, and then now my conclusion is that. Okay? So just being more precise with how you're saying it doesn't exist. So it says, usually it'll say, sometimes the question will say use infinity to explain, right? All right. So then the question was, does every square root? No, not square root. Does every reciprocal have that? No, because, and then let's take a look at this. So if I asked you a question, okay, we're going to take this aside. So if I had this one and I said the limit as x approaches 2, and I said, sorry, I'm going to change that up. I'm going to say the limit as x approaches 1 for the same function. Okay, what would I do with this one? Yep.
You would plug in 1.
That's it. We would just substitute in 1. This part here, so that's saying over here. So at 1, I'm just asking what that value is. So on both the left and the right side here, it'd be approaching whatever that value is. So if I sub in 1, I go 1 is 1 minus 2, so it's negative 1, so negative 1. So it's at negative 1, and that's that value right there. So the only place on this graph where the limit does not exist is at 2. Does that make sense? So let's just put that as an aside. For example, if I said the limit as x approaching 1 of the same function, that would equal 1 over 1 minus 2, which would equal negative 1. Let's just put that as an aside. Right? And that would be, say, that value here. Does that make sense? Right? So it's not any value on the reciprocal function. It's this specific value when it's an asymptote that it does not exist. Every other value on this reciprocal function is totally fine. Right? So you can find the value, you can find the limit for every other value, just not at 2. At 2 is where there's an asymptote, so something funny is happening. So if I said 1, I'd get negative 1. If I said 5, I'd go 1 over 5 minus 1/3. Right? If I said 100, it'd be 1 over 98, right? So whatever other value is, it is, because on the left and the right, as you're approaching, you're doing fine, right? You're going to find that value. It doesn't matter. Does that make sense? All right. So then let's try the next one. So that's, again, that's the idea of asymptotes, which I know that people were asking me last time as well, right? At the end of the lesson from last time, you're like, so what if? So hopefully that explains the infinity thing. Okay, so that's an asymptote. This next one, I chose this example just because people get confused with what it's saying. So let's read it carefully. It's a piecewise function. We've done piecewise functions already. It's just you kind of look at it and go, what exactly is this saying? So the first one, let's look at the first thing. So this is 2 things. So it's a piecewise 1 and 2. So for this piecewise function, I'm just going to drag it over here just so I can explain what's happening. I'm going to look at number 1 over here. So 1 is y equals 5. Okay, y is 5. So remember, we take the piecewise function, we grab each expression, each part, and make it into an equation. The second part is going to be this. So my second part is y equals negative 2. True? Right, so remember that from before. Piecewise functions, y is 5, y is negative 2. Now, this here says x cannot equal 3. This one says x equals 3. When x equals 3, when I said if I give you a value, a single value, so this part here is key. If I give you a single value, you give me a single value back. I give you one value, you give me one value back. When you sub that in, So you try to sub that in. I can't sub it because there's nowhere to sub it, but I'm going to get my value is still going to be -2. So my point is going to be 3, -2. Does that make sense? So when I give you a single value, you're giving me a single value back. Here, there's nowhere to sub it, so y is -2 no matter what. So this ends up being a point. A single value gives me a point. If I give you one value, you give me a point back. So that gives me a single point. And then you go, wait, are these the same thing? You're just going to give me 2 points? No. Look at what I said. So this is x equals 3. X equals 3 is a single value, single point. You give me a point back. That's understood. Here, when I say x does not equal 3, I'm not giving you a point. I'm giving you, actually, when I say x, I'm going to write this down. When I say x cannot equal 3, another way to write that is that x is less than 3 or x is greater than 3. Is that true? So this is actually this. When I say x does not equal 3, I'm saying then x is less than 3 or x is greater than 3. So I'm actually giving you a domain, right? So people go, the difference between this is that this is a bunch of points, both left and right. So I've got 2 arrows, 2 sides, and this is a single value. All right, so then that means, and again, I'm going to draw it. It doesn't ask me to draw it, but I'm going to draw it. So over here, okay, I'm going to draw just a little sketch just for myself. So what I've got is I've got the line y equals 5. So I'm going to have the line y equals 5, which will be here. So that's at 5. Okay, so y equals 5. But that is for when x is less than 3 or greater than 3, not equal to 3. So then I take my paper, I cut a little hole and say not there. Where is there? That's at 3. So I cut a hole here in my line. All right? And then that hole is this point. So it's at 3, -2. So then I put the point right here. So I put my point right there and I cut a hole in it. I didn't need to put a point. I could have just given this and said, well, there's my line. It's y is 5, but not there. So I could have had a line with the hole, or I can have a line with the hole and a point here. Good? All right. So now we can picture it. It doesn't ask us to graph it, but it's usually this part where you go, what is that saying? That's actually giving you 2 domains, right? So less than and greater than. Not equal to means it's both less than and greater than. Right? Or. All right, so then let's answer it. So if I know what it looks like, what I'm envisioning is that it's a line with a hole in it, and the hole is somewhere else. This hole, what limit am I looking for? Look it to see. So again, this one's 3, right? So that is significant because that's where the hole is. So does that hole matter? No. It's a trick. Right? So it's like, but I don't care where you put the chair. So if you think about this, I'm walking along, you took the chair, you moved it over, I don't care. We're still walking. So remember, it's about the destination, right? It's about the journey, not the destination. So it's the journey is, as I'm heading in from the left and the right, I'm still going to arrive here. It doesn't matter where the dot went. It just matters that as the journey, and then we both arrived here at that hole. So then my value, so my limit here, what's my answer going to be? Just 5. Right? So after all that, you go, yeah, so I just traveled and I went to 5. Good? Questions with that? Okay. So once you can picture it, I could have done 5x, right? That would have been a tilted line, right? So when with the positive slope with the hole in it at that point. Doesn't have to be horizontal. But this usually throws you off more. When I give you a single value, you're like, what is that? If I did 5x, you're like, oh, okay, it's a line, and there's a hole, and there's a slope, and you do all that. 5 throws you off because you're like, what am I, I've got nothing, right? So that's usually the harder one. You go, what does that mean? So it's a horizontal line at 5. There's a hole because you cut out at 3. So it's less than and greater than. The hole is over here, not relevant to what we're doing. As you're walking the graph left to right, you are arriving at the y value of 5. And that's it. Okay. So, right, so some special cases. So now we've done asymptotes, we're good. We've done this one here, which again just throws you off because the single values and the not equal to. All right, and the next one here, again, kind of a special case where you go, all right, I don't know what is happening with these guys. Why are these two special? They're special because of this. Okay, they're special because of this. The fact that the square root function only exists to the right of its starting point or to the left, right? It is a one direction function. So here I know that this function would start at -6, so dot here and to the right. It's not always to the right, it just depends on which way it is. Remember, we can do a reflection and all that stuff, but here we've got that. So I'm going to draw this here, and then I'll do this one in a second. So these two are matching. We're going to talk about both of them at once, but here. If I have -6, right, as my starting point, because I know that this has been translated left 6, right, so left 6. Here I'm asking for the limit as you approach 0. So as you approach 0, so again, think of it as a yellow line. I'm approaching 0, which is here, right? When x equals 0, I'm walking the graph from both sides. Remember, it's about the journey. We're approaching, 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 and we're going to meet up where? At, what value is that?
Root 6.
Yes, root 6, not 0, right? So root 6, so we're going to go as you're approaching it. How did you get that? I sub in x equals 0, so in your head, you're going to go 0 plus root 6, so root 6. Right, so as your y value there would be at root 6. Does that make sense? So we're going to go and then my y value there. All right, so that's easy. What happens if, same question, but I changed this? So this one goes to 0, which is that line. This one's going to go to -6. So then, okay, again, same idea. And this is the starting point at -6 heading this way. And what we're looking at is this. We are approaching, yes, what do you think?
Is the limit on the left side?
Yeah, the limit does not exist on the left side. So when you look at this, remember our definition, when we're walking from the left into the right, you're walking from the right here and the left, you can't because the function doesn't exist. So the limit doesn't exist here, right? So again, it's one of those limit doesn't exist. So you put does not exist, and then usually I say underneath domain, right? So domain. So over here, and I'll write that down with you here. So you've got this one, but the left one doesn't exist. Therefore, overall, what is my answer? My conclusion would be does not exist, exactly. Okay, so let's write that down, though. So whenever a limit does not exist, I usually say explain with the one-sided limits. So we're going to go the limit as x approaches -6 from the left. Now, over in this one, I wrote the function, right? So I said the limit of the function, the limit of the function, limit of the function. If you want to shorten it, I will let you, because sometimes the function I give you is pretty big. If you want to change that to f of x, that's okay. Obviously, if I gave you g of x, then don't change it to f of x, because I already told it. This one's f of x. This one here wasn't named, so I'll let you do this, because sometimes you go, okay, you know what, having to write this down over and over again, you can do that. So I'll allow you to do that. Or you copy it down like I did here. Does that make sense what I'm saying? Right? So you can write the function here. If you want to shorten it, because sometimes the function's longer, you can write f of x. So I'll let you just change it to f of x without having to say let f of x equal. Okay? So then you can say equals, and you're going to say does not exist, right? Usually I ask for students to put down domain. Right, just a one-word explanation. I'm saying the domain doesn't exist there, right? Right, so the graph doesn't exist. So just my domain, because it's restricted by the domain of the function. You don't have to do a big explanation, but the other one you can easily just say the infinity, like what we talked about here is infinity, negative infinity. Here I'm saying it doesn't exist. The domain, right? It simply doesn't exist there. Here, the limit as x approaches -6. -6 from the right, and then f of x. So if you want, you can use f of x. I'll allow you to do that. You don't have to. You can use the root x plus 6, but some people, when it gets longer, you want to shorten it. So this one would be approaching what? Y value? 0, yep. And then overall, my conclusion, so therefore, the limit overall for x approaching -6 in general. Remember, don't lose your function or your f of x, and you're going to say does not exist. Okay. Questions? All right. The next example is another piecewise. I'm just going through it one more time, 2 more examples just to go over one where we're graphing where there's asymptotes, and just want to point out a couple things, and then the other page as well. Yeah, question.
Why is it approaching 0 not -6?
You're asking for the y value or the x value?
The second one?
Yes. Am I asking for the y value or the x value? I give you the x value, you're getting the y value. Yeah. Okay? Yeah. Okay. So over here, we've got the limit as it exists, if it exists. Okay, sketch the graph of this function. So we've got, sketching the graph of the function, we've got 1 and 2, 1 and 2. Okay. Number 1 is just the parabola, right? So again, you don't have to show me this, but it is y equals x squared plus 3. We know that the vertex is at 0, 3, regular step pattern. Okay, you don't have to show me this, I'm just reminding you. 2, it's y equals 1 over x, etc., and this is, again, just in your brain thinking that part. Here we know that this is closed, open, right, open dot, and then this one here, right, this means closed. Okay, so just the little things you want to remember, and they're asking to find the limit as you're approaching 1, which is here where the 2 may or may not be open or closed, right? All right, next part. Let's graph. So I'm going to start with either one, it doesn't matter. I'm going to start with the parabola. So my thinking when I do this is that I start at the vertex. Whether or not it's part of the domain, I'll fix that later. I need the vertex at 0, 3, so 0, 3. The step pattern is regular because in front of the x squared is a 1. So I go over 1, up 1, over 1, up 3, over 1, up 1, over 1, up 3. So I've got the shape of it. And then I look at the domain. So as you're graphing it, you can do the domain and erase. You can go a bit faster, but that's my idea. So I've got the parabola. I'm asking for greater than 1. So greater than 1, but not equal to. So open dot. So that's this point. So at this point here, it'll be an open dot. So I'm going to erase that. And I'm going to put a nice open dot here. I'm just going to white it out in the middle because that way you can see it on the screen here, right? So that's an open dot. You don't have to white it out. I'm just making sure that you make sure it's clear what you're graphing. I do want you to put a dot, right? So don't just do it. So make sure it's big enough so I can see. It doesn't have to be giant, but just so I can see that you went through. And then you're just going through like that, right? So I can see what you graphed. I go back and erase these guys. So erase, erase, erase like that. Okay, erase those ones. And for my next one, so that's it for this guy, for my parabola. Then I'm going to do the reciprocal function. So the reciprocal function, the thing I wanted to point out here is that you have to graph as much as I'm asking for. So I'm asking for everything less than 1. I frequently get people who do this and they go, okay, but I don't need to graph all of it, right? And I'm like, yeah, you do. So I'm asking you to graph everything less than or equal to 1. So if I do that, I know that there's asymptotes, so it's going to be, I'm going to draw my asymptotes first. So my asymptotes are here, so I do a dashed line. I label it, and a dashed line here. Anytime you do an asymptote, you are also labeling it. Okay, so anytime you do an asymptote, you are doing this and you're also labeling it. Okay, so I want to see the label with the equation. Okay, so anytime you have an asymptote, you are also labeling it, so make sure you label it with the dotted line and the equation. Okay, so when you're doing your points, you know that it's going to be 1, 1. At 2, it's a half, and at a half, it's 2. Okay? The problem is some people stop